Okay, I'm going to set it up to record on this computer, and then I'm just going to hit start.
Okay.
Okay, well, we are live, so hopefully we'll have some folks who will be joining us shortly and have lots of great questions. So welcome. My name is Jill Molesky, and I do public relations for the Green Bank Observatory. We're so excited to have you here. I'm here with Dr. Ryan Lynch, who is a scientist at the observatory, and he is going to share with you some news and information about one of our latest press releases. And we're doing this on behalf of the Green Bank Observatory Science Center. So if you're unfamiliar with the Science Center, be sure to go to our website, check out all of the great resources they have, especially now while so many people are back in the home. We have lots of great experiments and STEM activities that you can do in the house. And yeah, without further ado, I'll go ahead and toss it over to Ryan, and he's going to share some of the science with us from this press release.
Yeah, thanks, Jill. So I'm going to throw a few slides up on the screen. Jill, can you see those okay?
Yep, I can see them.
Perfect. Okay. Yeah, so I'm really happy to be doing this today. My name is Ryan Lynch. I am a staff scientist at the Green Bank Observatory. My research interests are focused around pulsars and kind of fast transients of things in the universe that turn on and off very quickly, sometimes repeatedly. And I'm also a member of a collaboration called nanograv, which is using pulsars to try to detect gravitational waves, and that's what this AMA is about. So I just have a few slides here that I'm going to throw up to just kind of frame the discussion, make sure that we're all on the same page, and then I want to turn it over to all of you to actually ask some questions. So first thing is, what are gravitational waves? The purpose of getting here today is to talk about a really fascinating and exciting result that has to do with gravitational waves. Gravitational waves are ripples in space-time. I put that in quotes because that's a good conceptual way to think about them, but there's some terms there that may or may not be familiar. So when we talk about space-time, we're talking about the fabric of the universe that, according to Einstein's theory of general relativity, is curved by massive objects, and that's what creates gravity. So the way of thinking about this often is that you have like a bed sheet pulled really tight, you put something heavy in it, and it bends, and things fall towards it. That's kind of like having the sun being, say, a bowling ball, and then maybe the Earth being a little ping pong ball going around it, not to scale. Gravitational waves are ripples in that surface. Now, it's not actually a surface, but this is, again, just kind of a good conceptual picture that we use. Another way to think about gravitational waves, though, is that they actually cause the distance between any 2 points in space to change at a regular and repeating interval. That regular repeating interval is the wave part of gravitational waves. If you think about a wave undulating like this, it repeats over and over and over again.
Ryan,
but that change in the distance between any...
I just want to interrupt you for a moment. We're still seeing your title slide and the slide navigator. Just in case you were moving through the slides, it's still on that starting slide.
Okay. I was trying to move through them. This is when this sometimes happened before. So I'm just going to try and maximize things. Actually, no, stop. Share the whole desktop. Play. Is that better?
Yeah, so we see the first slide. Okay,
sorry about that.
No worries.
Technical difficulties. So what I was about to do, though, was talk about the pictures on the slide, so that's good. The one on the left is a representation, artist representation of gravitational waves that are being emitted by two black holes that are kind of orbiting around each other. And then the image on the right is just a little GIF that shows a ring of particles, black dots, that would normally be circular. But in this little animation, there's a gravitational wave passing through them. And so you can see that the distance between the dots changes. And in fact, it kind of gets tall and skinny and then elongated and short. So when you think about gravitational waves, think about the distance between 2 points changing due to changes in space-time that are caused by very massive objects with strong gravity like black holes. Okay, now I want to ask the question, what are pulsars? Because that's kind of the other half of the equation. And pulsars are the remains of dead stars that end their lives in supernova. So when a very massive star blows up, it doesn't completely blow up. It will leave behind kind of a very dense core. And that very dense core sometimes will collapse all the way to a black hole under its own gravity. But sometimes it kind of stops partway. And what we get is something called a neutron star. And all pulsars are neutron stars. What distinguishes them is that they emit beams of radio waves, and they rotate very, very quickly. So when that beam of radio waves points at the Earth, we get a little pulse radio waves, and hence the name pulsars. So the little animation down there in the left corner just kind of shows this in a cartoon form, and you can see that there's the yellow beam that's supposed to represent the radio beam, and then at the bottom, you can see that there's a little pulse every time that beam points towards us. And on the right is just a kind of artist representation of what one of these pulsars looks like with some of the different components labeled. For our purposes, I want you to kind of think of pulsars as clocks, because pulsars rotate really, really regularly. You will sometimes hear that you can set your watch off of Old Faithful, the geyser at Yellowstone National Park, because it erupts on such a regular schedule. Well, you can almost set an atomic clock by the regular pulsations that we see from pulsars. They're that precise. So they're these incredible astrophysical objects with all kinds of unique properties, but for our purposes today, think of them like clocks that are sitting out there in space. So what do pulsars have to do with gravitational waves? In fact, the first evidence for gravitational waves came from looking at pulsars, but that's not what we're here to talk about today. We are trying to use pulsars to detect gravitational waves by measuring very, very tiny changes in when the pulses arrive at our telescope. And we call this approach a pulsar timing array. So when you see the term PTA on the next few slides or in my discussion, that's just shorthand for something called a pulsar timing array. So the way this works is, remember, pulsars are like clocks. We have them distributed across the sky and throughout our galaxy. I want you to imagine that there is a pulsar above me and below me, okay? And then remember that animation of the rings that you saw from the gravitational waves. So I'm gonna back up a little bit to my pulsar dance. Okay, so pulsar above me and below me, gravitational wave passing through me. I get tall and skinny, and the pulses from the pulsar above me and below me arrive a little bit sooner than they otherwise would, because the distance between me and the pulsars has changed ever so slightly. Then I get kind of short and oblong, and then if there's some pulsars in this direction, those pulses arrive a little bit sooner. But the pulsars that are above me and below me arrive a little bit later. Okay. That's the basic idea. Gravitational waves that are hitting the Earth are going to cause this deviation in when the pulses arrive at the telescope from what we would expect if there were no gravitational waves. And the really important point here is that, it's the cat. The really important point here is that we see a particular pattern depending upon where the pulsars are in the sky and in relation to one another. And that was the whole point about the pulsars above me and below me. The pulses from them are running a little bit sooner, as opposed to the pulsars off to the side. Their pulses arriving a little bit later, and then vice versa as I get tall and skinny and short and elongated. Okay. So that's the quick explanation of how we're using pulsars to detect gravitational waves. This is a really hard experiment to do because the change in when the pulses arrive at the telescope compared to what we would expect without gravitational wave is only about tens of nanoseconds. And we're looking for a signal that takes years to detect. So we have to be able to track when the pulses are arriving at the telescope with tens of nanoseconds accuracy over the course of decades. But in North America, this project is led by a collaboration called nanograv, which I mentioned I'm a part of. And the main telescope that we use right now is the Green Bank telescope. Historically, we also used the Arecibo telescope a lot. Unfortunately, the Arecibo telescope collapsed a little over a year ago now. We still use data from the Arecibo telescope, though, so it's still contributing to our experiment. And nanograv is part of an international collaboration called the IPTA, which is made up of both the European Pulsar Timing Array and the Parkes Pulsar Timing Array. And then there's other collaborations in India, South Africa, China that are also contributing to this effort as well. So it's a global effort to use pulsars and radio telescopes spread around the world, including the Green Bank telescope, to basically use pulsars as a kind of galactic scale GPS system in order to keep track of these tiny changes in the distance between the Earth and the pulsars in order to try to detect gravitational waves. So why are we here specifically tonight? The reason is that we just had some really exciting results come out that I'd be happy to talk to you all about. So within the last couple of years, nanograv, along with the EPTA and PPTA, have reported that they see a signal in their data that seems like it's common to all of the different pulsars that we're observing. We haven't yet seen that particular pattern between pulsars that are separated on the sky that would really let us say for sure that what we're seeing is gravitational waves, but it's very much in line with what we would expect in the early kind of stages before we were going to make a really definitive detection. So it's really exciting because it seems like we're right on the cusp. And now, just last week, a paper was published which analyzed the combined data of the International Pulsar Timing Array, and that also shows a very similar signal. And again, science is all about repeatability and confirmation. If I see something and I think that that's the way that the universe is, that it reflects objective reality, someone else ought to be able to go out there and do the same thing that I did and get the same result. So the fact that we're now seeing all of these individual collaborations plus the combination of all of their efforts into a single big data set showing a consistent sort of answer is really exciting. It makes us really confident that what we're seeing is real. And now the only question is it really gravitational waves? We are optimistic that it is, but again, we can't say that for certain just yet. But if it is, then we should be really close within the next couple of years here to making a definitive detection. And I'm just showing the title of the paper if anybody wants to go check that out. So why does this all matter? What's the bigger picture? Now, astronomers historically have studied distant objects in the universe by looking at the light that they give off. We also sometimes detect little subatomic particles that go streaming through space and hit our atmosphere and kind of cause this cascade. These are called cosmic rays. But for the most part, for the whole of human history, everything that we've learned about the distant universe has come from light. And radio waves, microwaves, gamma rays, X-rays, the light that we see with our eyes, those are all forms of light. They're all forms of electromagnetic radiation. Gravitational waves, which were first detected about 60 years ago now, are a new type of messenger, to use kind of buzzword in astronomy these days. It's a new way that we can study the universe using gravity instead of light. And it opens up a whole new universe on the window on the universe, because things that might not emit light, like black holes, will emit gravitational waves. And so we can use gravitational waves to study things that we wouldn't otherwise be able to study. Pulsar timing arrays fit into this nice kind of spectrum of different types of experiments that can detect gravitational waves from different types of objects. In particular, pulsar timing arrays will teach us about the most massive black holes in the universe, supermassive black holes, these monster black holes that exist at the center of galaxies, and how they merge and how they grow, and what that means for the evolution and the growth of galaxies throughout the history of the universe, as well as probably some really exciting things that we haven't even thought of. Because whenever we go out, we look at the universe in a totally new way, we always end up finding things that were unexpected. And so kind of serendipity and the unexpected is a big part of why we're doing this as well. So that's all I wanted to do to kind of set the scene. I'm going to stop sharing my screen so I can see questions. I'm happy to throw some more slides, throw the slides back up if anybody wants me to go back to something. But with that, I want to see if any of you have any questions that you want to ask me.
Yeah, before we hop into the questions, I'm going to do a quick poll to see who is in our audience. So I just put this up on the screen here. I have to relaunch it real quick. Okay. All right. So if y'all can see this just real quick, just to let us know who's watching, who's here. We shared information on this presentation all over. Cool. So it looks like we're kind of evenly divided between science lovers, students, teachers. We got a few extraterrestrials, not surprised. Few scientists. Awesome. Okay, great. Thanks, everybody. Okay. So, okay, we had one pop up in the chat. And do you want me to go ahead and read this out loud to you, Ryan? Or says on slide number 2, you mentioned, you can just read it from there. And I see that another question came in through the question. So we'll go ahead and do the one in the chat first.
Sure. The gist of the question here, I think, is that the black holes are giving off these regular repeating gravitational waves as they orbit around each other. So eventually they're going to get merged. They're going to merge and they're going to get closer together. And so the question is, does that mean that the pattern of the gravitational waves that we see would change? And the answer is absolutely yes. So the very first detection of gravitational waves by the LIGO experiment actually saw the strength of the gravitational waves build up until the point that the black holes merged, and then you get some kind of residual gravitational waves being emitted after that. And you actually do see that the spacing between the peaks of the waves, or alternatively, if you want to think of it this way, the frequency of the waves was increasing as the black holes got closer to merging. So what sets the frequency of the gravitational waves, or how often the waves are coming in, is basically how quickly the black holes are orbiting around each other. And so as that changes, the frequency of the wavelength changes. Now for pulsar timing arrays, we're not seeing the actual merger event itself. We're seeing kind of the early stages as the black holes are orbiting around each other a little bit more slowly. So we won't expect to see a ton of variation from individual sources. It would take a while before you would actually see that. But in principle, you would be able to.
Okay.
And I was also see a question: do isolated black holes and make gravitational waves? If you have just a kind of a spherically symmetric object, even if it's really massive, spinning, it won't emit gravitational waves. So if black holes were bumpy, then they would, but black holes aren't bumpy. Pulsars and other neutron stars might be bumpy, in which case their rotation might give off a gravitational wave. But in general, we see gravitational waves from pairs of objects orbiting each other.
Awesome. Thanks, Ryan. Okay, so you might have touched on this a little bit with answering the first question, but another participant asked, what is the signal? Can you describe exactly what you're seeing?
I can try, but we have to actually go through a few different steps before we arrive at the data that we're analyzing to try and detect the gravitational waves. So when we look at a pulsar with the GBT, hi baby, I'm just gonna say goodnight real quick. Right, good night.
Good night.
Sorry, baby bomb. I didn't think you guys would mind. So when we actually look at the pulsar with the GBT, we don't see anything with our eyes because our eyes aren't sensitive to radio waves, but we can take the signals that we do pick up with the GBT and record them, record that data to a computer. We can visualize it, and what you would basically see is kind of like that little animation where you see nothing, then the pulsar points at you, and you see an increase in power at a range of radio frequencies, and that looks like the pulse. That's the pulse of the pulsar. What we actually are looking at when we're trying to detect the gravitational waves is what time do those pulsars arrive at the telescope, and how does that compare to what we would predict? So in order to do that, we have to know other things about the pulsars in order to predict when the pulses would arrive if there were no gravitational waves around. And then we take that prediction and we basically subtract it from the actual times of arrival that we measure. And then we do a lot of math on that with all the different pulsars to look for a common signal across different pulsars with a very particular kind of pattern, a correlation pattern depending on where they are in relation to one another. If you want to try and visualize it, though, again, the way to think about it is very tiny changes. Actually, they're not so tiny, but they take a long time to happen. in the distance between the Earth and the pulsar. So space is kind of actually shrinking and stretching a little bit. And that ultimately is what we're trying to measure. I hope that kind of helps to answer the question.
Okay. So we have another question. Is the new pulsar radio astronomy technique capable of showing the specific location of the black hole mergers? LIGO presently does not seem as precise. And thank you, great presentation.
Well, thank you for that, and thank you for the question. The answer is, unfortunately, that we're not going to have a good ability to kind of point and say that's where the black holes are. There's two different types of signals that we can actually pick up. One is kind of a background rumble from all of the different black holes throughout the universe, kind of just think of almost like a little bit of a static background that you can pick up on, this kind of rumble from all the different black holes. We call that a background signal, and that's probably the first thing that we're going to pick up. Eventually, we will have enough sensitivity to actually pick up a signal from an individual binary, so two black holes orbiting around each other, emitting gravitational waves, so a single source of gravitational waves. We expect that if things kind of progress in terms of our sensitivity in the way that we hope they will, that might actually come later on this decade. So it's not like it's way on down the road, but that's not going to be the first thing. But even then, we're only going to be able to kind of hand wave. It's coming from this general part of the sky. We're not going to be able to precisely point to it. And this is actually a really great opportunity for something which is a real hot topic in astronomy right now called multi-messenger astronomy. So we can say there's a black hole binary somewhere over here with these types of properties. Now, people who can localize things better, people with optical telescopes or gamma ray telescopes or radio telescopes that could pick up the other signatures from the black holes, but not the signals from the pulsars. They're indirectly inferring their presence. They can go look at this wide region of the sky, but they're not searching for a needle in a haystack. They know some of the properties that they're trying to find. So maybe they would look for something whose brightness is changing ever so slightly on the same kind of time scale as we see the gravitational waves being emitted at. And then they can say, that's the thing that you guys saw with gravitational waves, and it's right there in that galaxy, and then we can learn more about it that way too. So there's a lot of opportunities to combine techniques from electromagnetic telescopes and gravitational wave observatories.
Okay. So can you talk a little bit more about how you are a part of nanograv, and nanograv also happens to use the Green Bank telescope. So can you talk a little bit more about why we use the Green Bank telescope for research like this?
Yeah, so the Green Bank telescope is one of the best telescopes for looking at pulsars in the world. Pulsars are these little points of radio light on the sky, but we don't usually need to actually kind of image them or precisely say, they're right there in relation to other radio objects on the sky. What we really just want is a big light bucket that collects as much radio waves as we can in order to detect really, really faint objects or bright objects, but to detect them with really, really high precision. So the big collecting area of the Green Bank telescope is one of the advantages. Others that we can point it all over the sky. So we can see not quite everywhere on Earth or everywhere on the sky, because the Earth gets in the way when you're trying to look things that are really far south, but we can see 85% of what we call the celestial sphere. We can see lots of pulsars. And we can also see some pulsars that the other really big telescopes, like the FAST telescope in China or Arecibo telescope when it was still operating, couldn't see, because they're bigger and they're more sensitive, but they can't be moved around because they are so big. So it's really the sensitivity and the steerability, and then the excellent instrumentation that we have on the GBT that make it so good for this type of science.
Cool. Okay, we have two more that came in. So one is in the chat, and it's a little bit more technical. So I don't know if you can you see that there, Ryan?
I can. The question is, how would you distinguish the gravitational wave background signature of massive black holes versus that caused by the interaction of domain walls in the axion field, assuming it exists? I have no idea. I am not familiar with axion and like the theoretical physics about that kind of stuff very much. So I'm afraid I have to punt on that particular question. Sorry.
Okay, we'll note that for, maybe we'll ask around on that. Okay, so I'll ask one that came in the Q&A. So could the new JWST work in tandem with Green Bank to help locate signal locations?
Potentially, yeah. So it depends upon whether or not the types of black hole binaries that we hope we will detect gravitational waves from are emitting in the type of light that JWST can or will be able to pick up. So certainly there's some potential for that, and that's a really exciting new telescope that I hope we'll be able to use for these types of things.
Cool. So I'm going to bounce around a little bit between the Q&A and the chat. So someone appreciates your very clear explanations for non-scientists. Can you describe the details of the detection mechanism or the experiment?
Yeah, a bit. I'll try not to go into too much technical detail. So I mentioned that we take the actual observed times that the pulses arrive at the telescope, and then we take the predicted times, and we subtract those two. And if we understood everything, remember, gravitational waves are not part of our prediction, right? So we've left that out. So if there were no gravitational waves and we understood everything perfectly, then the difference between our prediction and the observed arrival times would be 0. And of course, that's not what we actually see. There are effects that we do our best to try and correct for, but it's imperfect. And so we kind of have to try and model that after the fact as best we can. So we have these noise models that are also part of this for each pulsar. And then, so we have the observed arrival times and the difference between the prediction. We call that a residual, if you're curious. So we have these residuals. We have these noise models for the pulsars that are supposed to capture other types of things that affect the signal or the pulsar signal that we have trouble predicting, but that we can kind of measure after the fact. But the key there is that they should be unique to each pulsar. They shouldn't be common to all the different pulsars that we see, because they have to depend upon the details of the pulsar itself or the exact path through the galaxy that the radio waves hope to get to us. And then we basically look for a correlated pattern. So we're doing a correlation analysis between these different residuals to look for a common signal between all of them. And that's what we have started to see is a common signal that's we can model with the same set of parameters. But what we have not yet seen is a spatial pattern emerge that says the pulsars in this direction are behaving in a certain way while the pulsars in this direction are behaving in a certain way. And that's kind of the last step. But it's a lot of Bayesian sort of techniques for model testing in the presence of noisy data, if those are terms that are familiar to you. And I think I'll probably not into too much more technical detail than that, but I hope that that kind of gives you enough of a flavor.
Okay, we have a few more really fun questions that have come in. So are you finding that when pulsars in some directions are running a little fast, pulsars in a perpendicular direction are running a little slow?
Yeah, kind of. So I don't usually personally think about it as running fast and running slow. I think one of the important things to remember is that the time scale over which we're seeing the gravitational waves have their effect is many, many years. So if you were to just go out on any given day and track the apparent arrival times of a pulsar, you'll see variations, but those are variations due to things that are not gravitational waves. Another way of saying this is that the wavelength of the gravitational waves that we're looking at is light years long, and so the time scale it takes for things to really change significantly is on the order of years. But if you had a single source of gravitational waves, then it's true that pulses in a perpendicular direction would arrive a little bit sooner, then a little bit later, then a little bit sooner as things were changing. But the pulsars in the perpendicular direction would be oppositely correlated there. So you can think of it as that they're running a little bit faster or a little bit slower. But again, the time scales are so long, I don't usually conceptualize it that way.
Okay.
They only appear to be running faster or slower. They're not actually running faster or slower. It's just an effect caused by the gravitational waves.
Are starquakes on neutron stars thought to be sources of gravitational waves?
Yeah, so this is something that we do observe indirectly in neutron stars. Sometimes the rotation of the pulsar seems to just kind of jump and do something weird, and we think that that has to do with basically the surface of the neutron star kind of maybe getting cracked or broken, or just transferring some angular momentum from the interior to the exterior very, very suddenly. If that caused a large enough kind of deviation in the distribution of mass within the pulsar, then it could potentially cause a very short kind of burst of gravitational waves. I don't think it would be very easy to pick something like that up, though. And things are going to kind of relax back to a more normal state afterwards, because what you need is a change and then some sort of asymmetry. So as things would relax back to a more symmetric state, then you wouldn't expect that. But if you do have kind of permanent deformations on the surface of the neutron star, little mountains on top of the neutron star, which probably wouldn't be very big mountains, they'd be little tiny hills, but they'd still be very massive. Then as the pulsar is spinning, those could give off gravitational waves and they'd be longer lived and easier to pick up. And that is one of the potential source classes for other gravitational wave experiments. Not the frequency range that we're sensitive to here, though.
Okay. So one from our dear friend Thomas, why are pulsar data files so big?
That's a good question. The answer is because pulsars spin really, really fast, so we have to record data really, really quickly. So pulsars spin, the fastest ones spin several hundred times a second, so the rotational period is like milliseconds. And so if that pulse only lasts for a fraction of that time, that's only, maybe hundreds of microseconds, then we need to be able to sample that even faster. So we usually record data every tens of microseconds, and that adds up really, really quickly. We're observing over a wide radio bandwidth too. So in a few minutes, we can easily record many gigabytes or tens of gigabytes of data, and you can imagine that starts to build up very quickly for an experiment which is using hundreds or thousands of hours over the course of many years. But it all has to do with the fact that pulsars rotate very, very fast.
Okay. How many pulsars have been discovered?
Good question. I think we're up to about 3,000 right now, if I'm not mistaken. It's in that ballpark.
Wow.
So probably only a few % of the total population in the galaxy, though. So we just kind of scratched the surface.
Okay. So I'm checking to see if we've had anything else come in. Anybody else thinking of anything based on all the awesome things that Ryan has been sharing?
I'll just follow up that last question and point out that only a small fraction of the pulsars that we found are actually suitable for the kind of experiment that we're doing with nanograv. We only observe about 75 right now. We think that with kind of like the best next telescopes, we might be able to find 200 that would be suitable. But that's out of the population, like I said, 3,000 that have been found. And we think there's probably something like 100,000 in the galaxy. And the reason is because we need pulsars that are really, really good clocks in order to do an experiment like this, because the deviation and the arrival time that we're seeing is just so small.
Okay, we've had another one come in. Are the sources of these gravity waves nearby or from the early universe?
Good question. So I guess it depends a little bit on what you define as nearby or not. We're talking about supermassive black holes. They're not going to be like in the local group of galaxies. So in that sense, we're talking about things that are going to be megaparsecs away, that kind of thing. It's an interesting question. When did the most massive black holes in the universe start to form? and would we eventually have the sensitivity to detect the very first ones? I actually don't know the answer to that off the top of my head. I think it would be difficult to have enough sensitivity to push out to those very, very most distant ones. But it's an interesting thing to think about. That's for individual sources, though. For the background, it's kind of the accumulation of all of the different supermassive black hole binaries throughout the universe, and obviously the nearby ones contribute more than the more distant ones. But in some level, they're all kind of contributing a little bit. There is a possibility, albeit it's more of a aspirational one, that using this pulsar timing array technique, we could actually detect what are known as primordial gravitational waves from the very early universe. We're talking about like just fractions of a second after the Big Bang during inflation. Probably pulsars are not the best way to detect those because they're just going to be so weak. There's probably better approaches to doing that. But it's something that remains within the realm of possibility, at least far enough down the road. And those would basically be the most distant sources of gravitational waves that you can imagine.
Another question that came in that is somewhat related to this one is, are pulsars found uniformly across the galaxy or clustered in specific regions?
We see them across large portions of the galaxy. There are a few areas where they tend to be found with higher density. One of those, what we call globular clusters, these are collections of very old stars that are kind of factories for making the very fastest pulsars, called millisecond pulsars. We see more pulsars concentrated more towards the center of our galaxy, and in the disk of our galaxy, just because that's where most of the stars are as well. So they kind of follow that pattern for the most part. We think that there should be a pretty large population or substantial population of pulsars in the very inner regions of our galaxy, near our galaxy's own massive black hole. And we really would like to discover those because we can learn a lot about our own local black hole that way by studying the pulsars that are around it. But so far, they have proven elusive, probably just because there's so much material between us and the black hole, and it or then the pulsars near the center, near the black hole. And the signals probably get what we would call scattered, which in this case kind of means more like it manifests in when they arrive. So you don't just get a very sharp pulse, it kind of gets smeared out, and that makes it harder to detect. And you can overcome that by going to higher radio frequencies, but then the pulsars aren't as bright. So you need really sensitive telescopes operating at those frequencies. A lot of people have looked, not yet found the kind of real close-in neutron stars that we would like to, but we think they should be there.
Okay. Another one that came in through the chat, the paper you showed said the gravitational wave background is isotropic, but does it have anything at all to say about the homogeneity of the universe?
If I'm understanding your question correctly, I mean, I think the answer is implicitly kind of yes. So this background signal that we think we'll pick up first, we're not expecting to be sensitive to differences in its strength depending upon where we look in the sky. It should have pretty much the same strength in all directions. Now, at some level, it's going to have to be a little bit different strength in different directions, of what we would call anisotropic. And there are people who have thought about that in ways you might be able to pick up on those anisotropies. But for the first order, it's going to be the same everywhere. And that is because at large enough scales, the universe looks the same in all directions, and we don't expect any one direction to necessarily have like more black holes. Now, there are clusters of galaxies that are closer to us, and if there's a lot of black holes there, then we may actually expect to pick up individual sources in that direction. And in that sense, you can kind of think of that as being inhomogeneity. It's one particular direction where you're seeing a stronger signal, but it's not the background signal. It's a strong source kind of peeking up above the background, if that makes sense.
Okay, we had a couple more pop in. So yeah, if you do have questions, be sure to put them in there because we'll wrap up before the end of the hour. So What is the life expectancy of a pulsar? Is it millions of years, or could the pulsar eventually evaporate?
So pulsars are not going to evaporate. Maybe you thought about that term because you've heard about black holes evaporating, this thing called Hawking radiation. You're not going to expect that to happen to a pulsar. But they don't emit radio waves that we detect as pulses forever. So pulsars can kind of go through two different life cycles. The first one, right after they're born, typically lasts about 10 to 100 million years, after which they kind of will die. There'll still be a neutron star there, but again, it won't be emitting radio waves that we can pick up. But sometimes the pulsar is in orbit around another star. And when that star kind of swells up to the size of being a red giant, the pulsar can start to pull material off of it. And that material spirals around the pulsar, kind of like water spiraling around the drain, and some of it falls onto the surface of the pulsar, and that spins the pulsar back up. It also makes the magnetic field of the pulsar, which I didn't talk a whole lot about, but pulsars have very strong magnetic fields, makes that weaker. And what we get out of that is something called a millisecond pulsar. So a pulsar that spins really fast, milliseconds to go through one rotation. But it's very, very stable because the magnetic field is weaker. There's not quite as much going on in what we would call the magnetosphere of the pulsar, which is this region where the magnetic field is very strong. We get charged particles and these types of things. And so those pulsars, these millisecond pulsars, those are the ones that nanograv is actually really interested in, and pulsar timing arrays, because those make the best clocks because they spin really fast and they're the most stable. And that's just a subset of the pulsar population. So I said we know about 3,000 pulsars. We know roughly something like 300-ish MSPs, maybe a bit more now. Millisecond pulsars is MSPs. And those millisecond pulsars will continue to emit radio waves effectively forever. Basically, for the age of the universe, they'll continue to emit radio waves. So they'll stick around for a long time, but that first phase of the pulsar's life cycle doesn't last as long.
Okay. Is it possible for gravitational waves to affect a pulsar signals prior to arrival at Earth?
Good question. So I'll get a little bit technical here again, but I think it's interesting. The gravitational waves are affecting the signal of the pulsar on its way, from the pulsar to the Earth. Again, the distance is kind of changing there. But in order to characterize that, you just kind of need to know the endpoints, the Earth and the pulsar. What we're currently doing right now is looking for the influence of the gravitational waves at the Earth, but there's also an influence of the gravitational waves at the other end. And if we knew the distance to the pulsars accurately enough, we could, in principle, recover that effect of the pulsars or of the gravitational waves at the pulsar. And there's some interesting things, because if you think about a single source of gravitational waves coming through the galaxy, it's going to hit some of those pulsars at different times, and then later on, it would, eventually affect the Earth. The issue is that we don't know the distance to the pulsars accurately enough to, if you're familiar with kind of the idea of interferometry, phase up our pulsar timing array. And it's hard to get those distances that precisely, because we would basically need to know them to some fractions, like a few light years. And there are some techniques, there's a few pulsars where you're able to get pretty precise distances, but to get that for all the pulsars in the array would be a little bit more difficult. But there's some interesting things you could do, and it would make you more sensitive if you could recover what we call that pulsar term.
Okay. This one's fun. Hypothetically, how close could an astronaut safely get to a pulsar? Would they be radioactive?
Yeah, this is one of my favorite questions, because I could go over all the ways that pulsars can kill you. Pulsars have strong gravity, but the gravity of the pulsar is not what would kill you first. You'd have to get pretty close to the surface before the gravity would start to tear you apart the way that you think of the gravity of a black hole tearing you apart. For a black hole, for a pulsar, if you tried to land on the surface, you get squashed into something much, much thinner than a pancake. But pulsars do emit very high energy radiation as well. So not just radio waves, also gamma rays and X-rays. And those would fry you long before the gravity would kill you. I have also heard, but now I can't quite figure out where I heard it. So I'm not as confident in what I'm about to say as I used to be. But I used to tell people that the magnetic field of a pulsar is so strong that it might actually be able to do weird things like the water molecules in your body. But someone was like, wait a minute, that doesn't quite make sense. I was like, I thought about it a little bit more. And then I was like trying to look up some things online and run some numbers. And I'm not quite as confident that part is true. So I'm not going to go through it as much. But the magnetic fields might still do something kind of strange if you got close enough. Magnetic field of a pulsar is strong enough that if it was at the distance of the moon, lots of bad things would happen. But one of them is that it would erase all the credit cards and hard drives and magnetic media that we have on the Earth. So the magnetic fields are much, much stronger than anything that we can produce in a laboratory here on the Earth. And I don't actually know what all the biological impacts of that might be. But definitely the gamma rays and the X-rays would be bad for you.
Awesome. That's a fun answer. Well, I don't see any other questions that have come in, and we've gone through about 18 questions, which I think is pretty awesome. So I'll give, just if you're thinking anything in the last few seconds here, I want to say thank you so much to Ryan for taking the time to do this. As you can see, he's an awesome communicator when it comes to sharing his science. And you might have even seen him or heard him in some podcasts or some other videos that we have up at our website. We will be sharing this recording afterwards. We'll be putting it up on Facebook and our YouTube channel. So if you want to use it as a resource in your classroom or anywhere else, you can find it there, or you can just reach out to us. We're always happy to help share our science with the community. So yeah, with that, oh, okay. No, I think we've got them all. Let me make sure. Oh, someone said thank you. Thank you. Not a question, but a statement. Appreciate it. Thank you very much. Awesome. Okay. Well, thanks again, Ryan. Thanks for everybody tuning in, and we'll catch you again the next time we do and Ask Me Anything.
Bye. Thanks. It was fun.